Hello everyone, welcome to another lecture for drug delivery principles in engineering. Today we are going to continue our discussion that we were having on polymers. Again, I just want to quickly remind you all that this drug delivery course will involve lots and lots of different interdisciplinary things. So, what I am doing currently is basically bringing you all up to par at what is the different areas and what do they mean for drug delivery. So, we initially talked about what is drug delivery, how is the drug distributed, what is the current methods, so pharmacokinetics of the drug, how the drug administered. Then we talked about prodrugs, which are quite a lot present in the market, almost 10% of the drugs are prodrugs. We then followed it up with what we would desire the current drug delivery fields to go in direction, so that the patients can have a much more better quality of life. And to go further into that, I am introducing some concepts of polymers, which are a big part of modern drug delivery fields, at least in research, and more products are coming out in the market for that. So, right now what I am doing is I am building up some of the basic concepts of polymers that will be required as we go along in the course. So, probably in the next 3 or 4 classes we are going to go jump into right core of the drug delivery fields, and all of this will be required for that. So, let us continue our discussion on polymers. So, what we learned in the last class, we talked about the ways for synthesis of the polymers, and mainly we discussed about a step and chain polymerization, how they are done, how this is done, what are their advantages and disadvantages, and all of that. While we were in the last class, this was the slide that we last left it at. So, talking about the molecular weight, and as I just said, typically in a polymerization you will have an average molecular weight, because the chains will be varying in terms of the molecular weights, each of them will have a different molecular weight. So, so we quantify this thing called average molecular weights. So, just now we are going to continue this discussion on this molecular weight. So, the average molecular weights in the traditional fields have been defined in several ways. Unfortunately, this is the case with most of the drug delivery areas, where you will find that literature has several different ways to define somewhat the same information that is being given. So, we need to know all of this, because when you read papers, when you read different literature on these, you will find different terms being used. So, now I am going to explain what are the most common terms being used. So, one of them is the number average molecular weight, and this is essentially defined as the average is nothing but the sum of the mole fractions of the molecule with different molecular weights. So, if let us say I have 3 different types of chains with 3 different molecular weights at different fractions. So, all I have to do is just multiply the fraction with the molecular weight of these 3 chains and then add them up. So, essentially further, let us say this can be changed as if Ni represent the number of moles with mass Mi, then the total average molecular weight will be nothing but sum of the Ni Mi divided by the total number of molecules, which is the summation of the Ni. So, note this is the arithmetic mean of the molar mass distribution. Ni Mi is also same as Wi, which is essentially nothing but the weight of the polymer having the mass Mi. So, we can also write the Mn and the average number average molecular weight as nothing but the summation of all the weights of the chain divided by the summation of the weights divided by their molecular weight. So, just an example. So, let us say if I have a polymer sample containing 9 moles with a molecular weight of 30,000 daltons and 5 moles with a molecular weight of 50,000 daltons, then in this case what will be the number average molecular weight? It will be nothing as just described above. All you will have to do is you will have to multiply the 9 mole by 30,000, and then you will add the 5 moles multiplied by 50,000 and then the total number. So, essentially we are using this formula. So, mole here is nothing but numbers. So, this is here, and then essentially you are dividing by the summation of the total moles, which is 9 plus 5, which will give you an average average molecular weight of 37,000. Let us say in a second example we have a sample of 9 grams of molecular weight of 30,000 and 5 grams of molecular weight of 50,000, in that case we will have essentially we will use the bottommost formula, which is essentially derived from the first formula, which is nothing but the total mass that is present 9 plus 5, and then we find out the total number of each of them, so fraction of each of them, so which is nothing but 9 gram divided by 30,000 for this particular sets of molecules plus 5 grams divided by 50,000 for the other set of molecule, essentially giving you 35,000 gram per mole. Another one that is used is a weight average molecular weight, and this is different from the number average. This is defined as MW is the summation of individual weights multiplied by their total mass, so molar mass essentially. So essentially this represents a weight fraction, and these are the formulas given here. This is essentially nothing but a second order average of the total distribution. So another example, very similar example to what we had done last time, but this time we want to compute what is the weight average molecular weight. So we have 9 moles with molecular weight of 30,000 and 5 moles with molecular weight of 50,000. In that case, all we have to do is multiply, use these formulas and essentially multiply the 9 mole with 30,000 square and then apply this formula, and we will get 40,000. Note this is very different from what you got last time, where you got close to about 37,000. So that kinds of highlights that the weight average molecular weight is different from the number average molecular weight. And again this can be represented in grams directly. This is going to make the calculation much simpler if you have grams there. So essentially in this case you will have to just multiply the grams with the molecular weight and add them up, and you get about 37,000. So as we said, note that the MW is typically always either greater or equal to Mn, and this brings us to the polydispersity index, which is a measure of the width of the molecular weight distribution in a polymer sample. So it is defined as a ratio between the weight average molecular weight divided by the number average molecular weight. So therefore by definition, if the polydispersity index has to be greater than or equal to 1, since we know that the MW is always greater than or equal to the number average molecular weight. But if it is a perfectly monodispersed polymer, only then you will have the MW equal to Mn, and in that case the polydispersity index will be 1. So greater the pi, greater it is than 1, broader is the distribution of the weights. So typically if we want any polymers, we would like these distribution to be narrow, because that will help us identify what are the different properties and how the polymers will behave. The more higher the pi, it is difficult to predict how it is going to behave in terms of its different properties. So as we can see here, in this case we see a fairly monodispersed polymer with a very narrow distribution. However, the other case we see quite a bit distribution. So in this case we can say that obviously the polydispersity for the 2 is much greater than polydispersity for the 1, and if it is of course absolutely perfect, we get a polydispersity of 1, which is a straight line in terms of the curves. Where do you typically get this? So typically in all synthetic reactions it is very difficult to get this, but however biology systems are very good. Typically the proteins that are synthesized by the body are all extremely monodispersed. So if you quantify any proteins present in a cell in terms of their molecular weight, you will get some sort of a distribution which is with a pi of 1 and a straight line in this curve. So how do we measure these molecular weights? I mean obviously these were all theoretical values, but how do we know what is the molecular weight of a sample that we are given with? And so there are a number of techniques to use this, and different techniques gives different results. Some techniques may give number average molecular weight, while some will give weight average molecular weight. So some of these techniques are listed here. We are not going to go through all of them, but some of the common ones that we are going to talk about is membrane osmometry, light scattering, viscosity measurements, as well as GPC and mass spec. So let us talk about membrane osmometry. This is a very widely used, and this gives a measure of the number average molecular weight. So essentially it is a colligative property. It is typically ideal for polymers in a wide polymer range, wide molecular weight range. So from starting from all the way from 50,000 to up to millions of molecular weight. So, and it is fairly simple here. All you do is you have two compartments which is separated by a semi permeable membrane that will allow the solvents to move through, but will prevent polymer to move through. And you can measure the height difference, because what will happen due to the osmotic pressure, the solvent will try to reach into the polymer solution to essentially make sure that the osmotic pressure is not there. However, as it further goes in here, there is also a height difference, so that creates a pressure, a reverse pressure as well. So, at some point it stabilizes, and you can fit it in equation from Vent's-Off equation. We are not going to go into the derivation, but you can use the Vent-Off equation to essentially get a relationship between the height difference here and the concentration of the polymer here, and this essentially you can then extrapolate to find this intercept here is, if you put it in the equation, is nothing but RT by divided by the number average molecular weight. And since you know R, you know T at what temperature the experiment was performed, and this line you have experimentally plotted, you can get the value of Mn through this intercept value. Then there are light scattering based methods. These are representative of the molecular weight determination. Again, these are number average molecular weight, and what they typically give you is also in hydrodynamic radius. So, how big these polymer chains are, not in terms of the molecular weight itself, but in terms of the actual diameter or the radius of them, the hydrodynamic radius of them. And typically these techniques work again between wide ranges from all the way from 10,000 to millions of them, millions of the molecular weight. And again, we are not going to go into the details of the electronics here, but essentially a sample is put in, a laser is hit on the sample at different angles, and the scattered signal is then used to amplify and see how much the polymer sample is scattering, and then once these equations are fitted, and gives you an estimate of what is the molecular weight that is being present in your initial tube. We can also have viscosity measurements. Again, these are widely used as well. This also represents molar mass. Lot of manufacturers will only actually specify intrinsic viscosity and not the molecular weights. And generally the relation here is, the higher is the molar mass, the higher is the viscosity. Here is a very simple experiment. You fill in a solution containing your polymer, and you basically time it as to how long it takes from the level to go from A to B, and this efflux time will basically can be used to then measure what is the viscosity. So, more time it takes, that means it is more viscous, which essentially also means that it has a higher molecular weight. So, again going further into details here. So, let us say if you use a pure solvent, the efflux time is T0. Once you have the solvent containing a certain concentration C, let us say the efflux time is Tc. Then there are several types of viscosity that are mentioned. You can go through these. The one that is very widely used is the intrinsic viscosity, which can then be computed through this particular method by extrapolating it to the concentration 0, and from the Markov-Cohen secondary equation we know that the intrinsic viscosity is related with K with M as intrinsic viscosity is equal to K multiplied by M to the power of A, where K and A are again experimentally determined through several experiments. And then another very widely used and very powerful method is the gel permeation chromatography, also called size exclusion chromatography. And what it is you take small volume of your dilute polymer solution and you inject it into a column that is packed with beads. These are porous gels, typically with the diameter in ranges of angstrom. And what happens here is you have a column which is packed with beads which are porous. So, these beads have small pores going through them. So, if the polymer is small enough to enter these pores, the polymer then expands. If I zoom into a bead, so you have these pores going through these beads, and if the polymer is small enough, it goes and interacts into these channels and it has to traverse all the way down through these pores. So, whereas the big polymers will essentially just come and go right through from the outside because they can't enter these pores. So, what essentially happens is the larger polymer molecules will start coming in out first, whereas the smaller polymer molecules will take lot more time because they have a lot more path to cover through these beads. So, and that essentially results in separation of these polymers. So, the first one to elute is the largest molecular weight, and then as time goes on smaller molecular weights come out. So, you can then plot a concentration against the elution volume, which will give you also a qualitative indication of what is the distribution of these, and not only that, you can actually then separate them out into different fractions to make sure that you can get different molecular weight fractions, and then that will also result in narrowing of your particular polymer distribution. Okay. So, that is in terms of the techniques for measuring the molecular weight. Next we are going to talk about the crystallinity, which is again a very important property when we talk about drug delivery. So, when a polymer is slowly cooled from a melt state, it typically forms an ordered structure. These are similar to crystals. Such polymers are called crystalline, or they can be semi crystalline, and polymers with the regular compact structures and strong intermolecular forces like hydrogen bonds or ionic interactions have a very high degree of crystallinity, and essentially what it means is as the polymer chains are interacting more and more, they are coming closer and closer and packing very well, and that results in the polymer being highly crystalline. So, as crystallinity increases, the polymer becomes more opaque because the chains are very close now and it does not allow the light to pass through, it causes scattering of the light. So, something like Teflon will look white because of this reason, and if you heat this polymer up, what will happen is more and more heat energy will go into this your polymer sample, and there will be a temperature Tm, which is called a melt transition temperature, at which all the crystalline regions are melted and the crystallinity disappears. So, as the degree of crystallinity increases, so if you have more and more intermolecular interactions between the chain, the melt transition temperature also increases. So, the crystallinity can have major effects on several properties. It will change the mechanical properties because more crystalline it is, the more compact these chains are. So, increased stiffness and it will become less flexible. The diffusion rates will change because now these chains are very tightly packed. So, because they are so tightly packed, it will be less permeable to diffusing molecules through it. The rate of hydrolysis will change because now even the water will find it hard to go in and break these interactions apart. So, the rate of hydrolysis will also become slower. And then like crystallinity, there is also amorphousness. So, not all polymers exhibit crystallinity. So, there are polymers that are amorphous. So, some polymers does not really form any order structure even though you can cool them down from melt state, and these polymers are called amorphous polymers, and they sometimes are also referred to as glassy polymers, and they essentially lack any kind of crystalline domains that scatter light. So, they are typically transparent. On heating, amorphous polymers are transformed into a very hard glass, so which is a transparent to a very soft flexible rubbery state, which is essentially just molten chains flowing around. And this loss of this amorphous structure to more a rubbery solid state, rubbery flexible state is called glass transition temperature. So, at this temperature it will go from hard glassy state to a much more rubbery state. So, very similar to Tm, but this is more defined for amorphousness. So, again how does this glass transition temperature affects properties? So, since the motion of polymer chains will increase above Tg because it has now become rubbery, only the above the glass transition temperature you will have lot more motion, lot more diffusion through it. It will change lot of sub properties like heat capacity, density, permeability, dielectric constants, they all change very abruptly at Tg. Polymers are typically brittle below Tg. So, a good example is a rubber ball. If you cool it down with, let us say, with liquid nitrogen and try to throw it, with the impact it will just completely shatter. whereas otherwise if it is above the Tg, which is at room temperature, even if you throw the rubber ball down, it is fairly elastic and it will not break. So, depending on the usage, proper polymers can be chosen. So, let us say if you are looking for breast implants, you want those to be more rubbery, more elastic. So, silicones are used which have extremely low Tg and Tm, and so they are always fluid at the body temperature, which is 37 degrees Celsius. And similarly polystyrene, PMMA, these are glassy state at room temperature, and so they are hard, and above if you heat them up above 100 degrees Celsius, they are essentially much more fluidic. So, chain mobility is again very critical for diffusion. So, below Tg the diffusion is much slower compared to above Tg, and this again, so these are ideal circumstances. Typically in the nature you would not find polymers which are completely crystalline or completely amorphous. They typically exhibit both to certain extent. So, so an example here is the polyethylene terephthalate, which essentially is abbreviated as PET, and this has several crystalline domains depending on how it is cooled. So, you can have as much as from 0% to 55% crystallinity depending on how this is being formed. So, if you completely cool it very quickly, it will result in very amorphous structure. If you give it some time in cooling, very slow cooling, let us say half a degree Celsius per hour or something like that, the chains will have enough time to come in contact with each other, interact, form strong interactions, and result in crystalline structure all the way up to 55%. So, plastic beverage bottles are PET. So, do you what do you think they are? Are they crystalline or are they amorphous? So, remember what did I tell you earlier regarding what happens to the light scattering, and in general how elastic and soft it becomes. So, yes, since we know that these plastic bottles are transparent, they cannot be crystalline because crystalline structures scatter light and do not let the light to pass through. So, they will be more opaque. So, the plastic bottles as we know is transparent, made of PET, so it has to be amorphous with a low degree of crystallinity. So, by cooling slowly you can get more ordered crystalline domains as we talked about. So, the same PET you can get with a high degree of crystallinity, which is then used in textile fibers and tire cords, and the same one can also be used in plastic bottles. Just the only difference is how fast they are cooled. And then finally, how do you measure what is the Tg and Tm of a polymer sample that you are given? So, this is regularly done using differential scanning calorimetry. And so, what is done is you have a reference pan and you have a sample pan with your polymer, you measure how much heat is being given to each of those and figure out the Tg and Tm on the basis of that. So, as polymer undergoes transition due to heating, so essentially what will happen is the heat is flowing, the temperature is increasing as more and more heat is flowing. At the Tg, it will cause a lot more absorption of heat to essentially melt these chains up. So, the heat flow increases, then it becomes constant again, and then when it close to Tm, you need further induction of heat, so that the polymer chains can then be separated from the intermolecular forces, so it goes further up. So, these transition points you can then determine for all the samples that you have, and that will give you an idea of Tg and Tm. A quick note here is, what do you think is Tc? Okay, so this we have already discussed, but what is Tc? So, Tc is nothing but, because you are slowly heating it up from the transition from here to here, this is a point where more and more intermolecular chains are coming in contact, because see here the sample was very cool, and so these molecular chains had no interactions because they were kind of solid, but at this point these molecular chains can now move around, they have become glassy, and these can then interact and essentially form crystalline structure, which when further heat is given then breaks apart and essentially leads to the Tm temperature being reached. So, I am going to explain this curve further. This is not a trivial curve. So, let us see. So, the heat capacity of a system is the amount of heat needed to raise its temperature by 1 degree Celsius. So, if the material is not changing heat capacity, this curve will look like a straight line, right, because you are flowing a constant rate of giving a constant energy per second, and then the temperature will continue to increase by 1 degree Celsius at its particular heat capacity. So, in an ideal circumstances you should have a straight line like this, typically metals show this. However, we know that the heat capacity of the polymers is usually higher above the Tg, and so that is why you see that initially it's a straight line. At the time of Tg more heat is required, so it takes up more to basically melts it, and then the resulting polymer is above Tg, and so it has a higher heat capacity. So, that is why you need more. This differential that you get is because now the temperature has changed its property, its heat capacity as well. And then the crystallization is an exothermic process. So, now these chains are coming in contact with each other and forming bonds, could be van der Waals, could be hydrogen bonds, and this releases heat, and because it releases heat it does not need any external heat flow that we are giving. So, the external heat flow requirement comes down, but once the chains are formed it goes back up. So, we are still talking about the same polymer with the same heat capacity, so it is still at the same level. And now as you go along the melting of the polymer chains, to break them apart you need to give further energy, because earlier they had released energy, now to give the further energy to break them apart, and so this needs to go up, and by this time it becomes completely mobile and you have a constant heat flow required to raise the temperature. So, I hope this is now clear as to how this works. So, what are the different factors that affect Tg? So, molecular weight is one of the major factors, because in a polymer chain the end groups are the ones that are highly mobile, and so if you have low molecular weight for the same amount of polymer you have lot more polymer chains, and so they have lot more energy to move around, and so you will have a lower Tg. But if you have a higher molecular weight these chains can entangle and that will result in a higher Tg. If you have bulky side groups that will hinder chain motion, if it hinders chain motion it will increase the Tg. So, if you have PMA versus PMMA, PMMA is nothing but an extra methyl that is present on the PMA chains. So, which one of this will have the higher Tg? It will be PMMA, because it is now having another CH3 that will hinder the motion of this chain. If you have strong molecular attractions between them you will have a higher Tg, because now they will tend to interact with each other and will essentially decrease the motion. If you add dilutant and plasticizer at the time of these polymer heating, this increases free volume and thereby the chain mobility will increase. So, this is one of the way that you can lower the glass transition temperature of a particular polymer, and generally if it is higher Tm it basically means that that polymer will also have higher Tg. Okay. So, we will end right here, and we will now in the future classes we will go into more into biomedical polymers. So, this is a general discussion we gave on what polymers are. Now, we are going to go specifically into what is the properties for the biomedical polymers, bioengineering polymers that we will use for drug delivery. So, see you next time. Thank you.